Hello everybody, welcome to today's lecture, carrying on with logs and exponentials. So today we're going to be looking at a topic called reduction to linear form. It might be a bit different to a lot of the stuff you've done on logs and exponentials. Hopefully, if you've seen the email, you've printed off the worksheet that goes with it. If you haven't got access to a printer though, don't worry, you'll still be able to do some of the tasks, just not quite in the same way. Before we get started, this PowerPoint is quite long and you've done quite a lot of it if you did the last lecture already. So I'm just going to show you a quick way of navigating around the slides so that if you need to dip in and out of the PowerPoint, you don't have to scroll through everything to get back to where you started. Okay, so a few buttons that will be useful. First of all, in the top left corner, this button here always takes you back to the front slide here. In the top right corner, this tells you the slide number. So if you're ever trying to find whatever slide I'm on, just look in the top right corner, it will tell you what slide you need to go to. So the next thing, if you're using this on a computer, you should be able to right click on here and there is an option for go to slide. Okay, and you can go to any slide you want down here. Okay, you can scroll down to the bottom. Unfortunately, it only goes down to 60. There's more than 60 slides in this. If you need to go past 60, you can click all slides and then you can get even further down here. You can get all the way to the bottom if you wanted to, and you could just click on one of them and go straight to that slide. Okay. So let's get started then. Just a reminder about where you can get these resources from in case you haven't got them already. If you're a student at Bilbao College, you can go to this link here, parkermaths.com/year 1 maths, and you can go to lecture 2 in week 25 and download all the resources for this. If you're not a Bilbao College student, you can still get the resources from this link here, parkermaths.com/remote learning. If you have any problems during the lecture, anything you don't understand, or in this lecture you might find you have some technology difficulties, please do email me during the lesson and I'll try and resolve them as quickly as I can. Okay, so last lesson we looked at exponential growth and decay. Today we're going to be looking at a topic called reduction to linear form. So imagine we've collected some data and it looks like this. We've got x values and y values. It doesn't matter what the data is for at the moment, and we want to know, does this data fit an exponential model? Maybe it does, maybe it's a different kind of model. So we've got x and y values, we could try plotting them. If you did that, you'd get this curve you can see on the screen. Now, it kind of looks like an exponential curve, but it could maybe be a quadratic or a cubic, or maybe it's even something else that we don't know. We might be fairly sure it's exponential growth, but even if we are really sure it's exponential growth, we still don't know the equation of the line that would best fit this data. And that's finding the equation of that line is what this lesson is going to be about. So, in order to plot these graphs, we need to think about a different way of plotting graphs to what you might be familiar with. Most of the graphs you'll have drawn so far in your life as a mathematician will be what we call linear graphs, well, not linear graphs, but they'll be on a linear set of axes. What I mean by that is that the intervals that you're going up in along both the x and the y axis, it stays the same distance apart for each one. So between 1 and 2, we go a distance of 1. Between 2 and 3, we go a distance of 1. And it's the same between any two intervals as we go up. It's always the same distance apart. And it's the same on the horizontal axis as well. Another way of drawing a linear axis is like this. It doesn't have to be going up in ones. It could be going up in fives on one axis and twos in the other. But the key thing is that the difference between this dash and this dash is the same. It's 5 as it is between these two dashes. So it is still a linear scale. Okay, it's just stretched out a little bit. What we can do though is we can have a different kind of scale on one or both axes. What we can do is we can use something called a logarithmic scale. Now, in this graph we've got here, this is actually called a semi-logarithmic scale because only the vertical axis has got a logarithmic scale on. The horizontal axis is still linear. We've still got the same distance between them. So you might think this looks a bit unusual. What's going on with this axis here? Well, what we're saying is the interval between 0 and 10, the amount you'd go up in, is different to going 10 to 100. And then 100 to 1000 is different again. And so this is really useful if we have got to cover a long range or a large range, sorry, in our y direction, in the vertical direction. We can actually map these. If you're wondering why it's called logarithmic, think about these numbers on the left here in red. 10 is 10 to the power 1, 100 is 10 squared, 1000 is 10 cubed. So we've still got that 1, 2, 3 and 4 going up the y-axis is just a little bit different. So, to help you better understand how you would plot points on a pair of axes like these, just want to consider, let's say let me just get a different colour pen. Let's have a think, where would 55 be on these axes? Because think about it, 10 to 100, you would expect maybe that 55 would be halfway, because 55 is halfway between 10 and 100. But unfortunately that's not actually the case. So let's have a think about how we could figure out where would 55 be on the y-axis here. Well, notice that this dash here is 10 to the power 1 and this dash is 10 to the power 2. Any dash that we make in between here would be 10 to the power of something that's between 1 and 2. So what we would want to know if we want to be able to plot 55 is 10 to the power of something is 55. What value would that be? Well, let's be a bit more sensible and use a letter up here. 10 to the power of x equals 55. We could solve that using logs to get x is log base 10 of 55. And if we do log of 55, that's 1.75, or sorry, 1.74. So it's almost 3/4 of the way up. So although intuitively you might think 55 is halfway, 55 would be here, almost 3/4 of the way up. So it's quite tricky to plot things on a log scale. Fortunately though, we've got a bit of a shortcut we can use in order to do it. And that is, instead of having a y on the axis up here, we can just change what the vertical axis is labelled as and call it log y. Because then we can just have the values 1, 2, 3 and 4 up the side. Because log of 10, which we had here, is 1, log of 100 is 2, and so on. Okay, so instead of having x and y on our axis, instead we've got x and log y. Okay, now it might not immediately be clear what the use of that is, but as we start to look at an example it might become clear why it's really helpful to be able to do this. Okay, one last thing, notice that now we've changed it to log y, we're back again to having even spaced intervals on the vertical axis. So we're going to move on to the first example now. Hopefully you've printed off the graph paper so that you can have a go at this using pen and paper, which is the best way to do it. If not, you could always pause the video. There's a link here that you can click on and load the graph paper up, and you can print that off and you can use it for these two examples. There's also a link to the exam questions that we're going to get to at the end of the lesson as well. Okay, so if we had our original data here like this and we wanted to plot it on these axes, what we would need to do is plot the x values against the values of log y, which means we would take these y values in this row and we would calculate log y for each entry, and that would help us get our pairs of coordinates. So here's the same data, here's some data in a table, and we're going to have a go at plotting a graph with this data and see what happens. We're going to plot the log graph of it. Okay, so I'm just going to give you a few seconds, just have a read of the question, see what it says, and then I'll talk you through how to answer it. Okay, so key things to look out for in this question then. We're going to verify that the model of this form is of this form: n equals ka to the power of x. When we have something to the power of x, this is an exponential growth equation. We're more used to seeing it as e to the power of x, but you can have any number here and it will still be an exponential growth equation. Okay, so the first thing we're going to do is start with that equation. Sorry, I forgot it. N equals ka to the x. Still got a white pen on. Okay, and what I'm going to do, I'm going to rearrange this and show you why it will be useful to plot it on a log scale. Okay, so the first thing I'm going to do, I'm just going to take logs of both sides. So I'm going to get log n equals log of k a to the x. Now I'm going to give you a chance to have a go at this along with me, because you might make a very common mistake that people make. Don't worry about it if you do, but if you make that mistake, I think you'll see where you went wrong, and you'll be less likely to make it next time you do it, rather than just watching me do it. Okay, so from this step here, what I would like you to do is use two log rules. Okay, I want you to use the power rule and also the addition rule, or the product rule, where we've got a product in here. Okay, so I want you to pull this log apart using both of these. Maybe not in this order, I'll leave you to decide what order you want to do everything in. Okay, I want you to take this side here, nothing to do with the left side, and just apply these two rules in whichever order you see fit. Okay, it might take you 2 lines of working out, you might be able to do it in your head in 1, it's up to you. So I'll give you a few seconds to have a go at that. Okay, I'm going to finish this off in a minute. I've just noticed something on the PowerPoint. I don't know if you've got exactly the same version as me. There's a bit of a mistake on it. It's not really to do with any of the working out. It's just what I've labelled things, messing about with letters really. What I would be really helpful if you could do is this t and this n, just replace them with x and y. And this equation here should be y equals k a to the x. I'm sorry if you spotted that already and you were a bit confused as to what I was doing and you'd looked at the working out. That needs changing, which means I'm just going to have to change it on the next page as well. So rather than using n and t, I'm just going to use x and y, because that's what I've done for the rest of the working out. So I don't know why I've changed it there. So I'm going to start with y equals k a to the x. And I do apologise if you're the kind of person that hates crossing things out in your working out. So log y equals log k a to the x. Okay, now I'm going to pull this log apart. The most common mistake people make is the fact that this power here is only attached to the a, so you can't simply bring this power down to the front. If you've done that, you've not quite done it right. You'd need brackets around this to do that. So what we would really have first is, if we use the addition rule, we could write it as log k plus log a to the x. So I've pulled those two apart, and then now that I've pulled those apart, I can use the power law here. So I can write this as log k plus x log a. And you might look at that and think, well, what was the point in that? It doesn't seem very helpful at first glance. But what we'll get if we have a look at this a bit more carefully is we can see that this is actually the equation of a straight line if we choose our axes correctly. So I'm still going to have, I've got an x here. So on the horizontal axis, I'm still going to have x. But I haven't got y here, I've got log y. So what I'm going to do, rather than have y on the vertical axis, I'm going to have log y. Okay, and if you think about the equation of a straight line, it is of the form y equals mx plus c, and we can draw parallels with what we've got here. Instead of our y, we've got log y. X here, that's still x, but then you have plus a number. Well, log k is just a constant, so that is just the plus something. That is our intercept on the vertical axis. And here we've got log a, which is just a number multiplied by x. The number you multiply x by, This is just gradient. Okay, so what we've been able to do by taking this first equation of an exponential and rearranging it by taking logs, we end up with something that is of the form of a straight line, because we can do more maths with straight lines than we can do with exponentials. Okay, so here's a neater version of that. Okay, right, so what can we do with this then? Well, we can now plot a straight line graph to represent our data. What we're going to do is, instead of plotting y against x, we're going to plot log y against x. And if we do that with the original data that we've got, and an exponential model is the right fit, we will find that our data gives us a straight line. And then with that straight line, by finding the gradient and the intercept, we can actually find out the equation of the exponential curve. We can find the values of k and a. Now, there's a lot going on at once here, so don't worry if at the moment you're feeling, wow, this is going a little bit over your head. As we go through the example, it'll hopefully start to make sense when we start to put some numbers into it. Okay, so the general idea is this. We're going to take an exponential curve, and by rearranging it to write it like this exponential curve will become a straight line. And the reason that is good is because with a straight line we know how to find the intercept and we know how to find the gradient. We've been doing them for years. Okay, so by finding the gradient and the intercept, it will allow us to find the values of k and a, and we'll be able to find out the equation of the original curve. So, first thing we're going to do is we're going to take our original table of values and we're going to calculate the values of log y. Now, you can, if you want, literally just type these into your calculator. You can do log of 0.5, log of 1, log of 1.5 and so on, and get your values out. What you might want to do instead though is do it a slightly different way on your calculator, which can save you a little bit of time. Now, you're under no obligation to do this. You don't have to use this function on your calculator, but it's nice to know that it's there and it might save you some time. Okay, so I'm going to give you a chance to do this along with me, just so that you've had a go at it. If you decide it's not for you, then fair enough. Okay, so with your calculator on the main menu, we're going to go into mode number 7, which is table. In the first column here where it says y1, we're just going to put log of x. Now ignore the fact that it's x here. It's actually going to calculate log of y, but you have to just use x here. Okay, essentially what it's going to do, it's going to think of this as log of the output, sorry, log of the input. So you're going to take each one of these values, your calculator's going to log it for you, and it's going to display it nicely in a table. So we've put log x in this first column here. If you've got anything in these just by chance, you can delete them. Then next we're going to go into set, which is F5, and we're going to set up the x values. Start and end values will be the first value and the last value in our table. So the start value is 0.5. and the end value is 4.0, or just 4. The step bit tells you how much you want to go up in each jump, and we are going up in 0.5s each time here, so I'm going to put the step in as 0.5 and then press equals twice. Now when I press this table button here, the x values will be in this column and the y values will be in the column on the right, and if I want to, I can just scroll down through those and I can write them all down without having to write anything down. Okay, so I calculated them earlier though. These are the ones that I got when I did it. And so what we're going to do now is we're going to plot these values on a graph. And hopefully, if an exponential model is the right one, it will make a straight line. So, taking your table of values, you're going to plot the points. Once you've plotted your points, I want you to try and draw a line of best fit through them. Okay, this one is pretty nice. It's pretty close to the points. They don't perfectly go through it, but they are quite close. So I'm going to give you about, I don't know, 3 or 4 minutes to have a go at that. If you've got graph paper, great, you can do it on that. If you haven't, go back to slide 49 and you click on this link here where it says Desmos page. it'll take you to a Desmos page, which I'll show you in a minute. Okay, so if you are having a go at this on pen and paper, you can just crack on now. You don't need to listen to what I'm going to say, but for those of you that can't, I'm going to go through this on Desmos so I can show you how you can plot your own points, so that when you do the problem that goes with this one, you'll know what to do. So if you click the link, it will load up this page here. Okay, for this example, I've put all of the values in for you. If these values here are just the original X and Y values. Now, if you turn those on by pressing that, you'll only see the first one on the screen. Don't scroll out because you don't need to see these. These are all really big values that go off there. These axes I've set up for the log graph. Okay, what you would normally do, you would take these Y values, okay, and you would do log of those Y values and put them into this table here. So all I've done here is take a log of these and pop that into here. Okay, then if I turn those points on, there we go, that's what you'd get if you plot them. Now, it'd be better if you could plot them for yourself, but this is just a backup really. Okay, and I've also set it up so that if you turn this line on here, it will give you a line of best fit. Okay, this line of best fit will always be for whatever these Y values are in here. So if you got these wrong, you'd have a weird and wonderful line of best fit. Okay, so if you haven't got your own graph paper, I would like you to load this up and just become familiar with this sheet, because in the next question when you're doing it for yourself, you're going to get a similar one. So just make sure you kind of understand how to turn off and on all the lines and things like that. Okay, somebody's just asked me to go over the calculator ones again. It's probably a good job actually, because I've made a mess of it, which I've just realised when I've put the values in here. We're supposed to be doing log of the Y values, and I typed in the X values, which was a bit stupid. The method for finding the values was right though. We do still want to put log X in here. We can't write log Y in. But what I did wrong was in the set bit in here, I should have done the start value. Oh, in fact, you can't even do it for these ones. You literally just going, because these ones don't go up in nice intervals, you're just going to literally have to do log of all of these on your calculator. So sorry for the little bit of confusion there. What you're going to do is just do log 4, log 7, log 14, and so on. You will have to do this one by hand, I'm afraid, if you wanted to find the values for yourself. Okay, so just to recap what you should be doing now then. Okay, first of all, draw yourself out this table, fill in the log values, plot them on some graph paper, or take a look at the Desmos one. Okay, and then draw yourself a line of best fit. Okay, so I'll give people a few more minutes to have a go at that. Okay, what would be very helpful is if anybody who is doing it on graph paper, if you could just send me an email when you start to get towards finishing the points or something, I'll kind of get an idea of how far people are along. Okay, I'm just seeing people are there or thereabouts now. I've had a couple of people say that they're finished. Okay, so now we've got our line of best fit. We're going to find out the gradient and the intercept. Now, it's important to know with these kind of graphs, if you're drawing them by hand, there's going to be a margin of error involved. And that doesn't matter too much for the purposes of what we're doing. And when you collect data in general, there's probably going to be some kind of errors in that data as well. So, you might not get exactly the same values as I get, so don't worry about that if you don't from your graph. Just to get the intercept, we just need to kind of look that up on the graph, really. Okay, I've put the y-intercept up here. Be careful about what you call it, because really it's the vertical intercept rather than the y-intercept. The value I've got down here is kind of, each one of these dots is, each interval is about 0.2, so I've gone for round about 0.35. I can also calculate the gradient of this line as well. So when it comes to calculating the gradient, I don't want you to use points unless that point is precisely on your line of best fit. If it is, great, use the point. Essentially, all you need to do is choose 2 points somewhere on your line and draw a line across and a line up to make a distance up and a distance across for your gradient calculation. Now, the further apart you can make those 2 points, the better, because it means you can be a little bit more precise in your readings. Okay, hang on, I've just got an email. No, it's nothing, don't worry. Okay, so I've picked 2 points here. I've chosen these two because it pretty much goes through the grid lines at those points, which means I can get nicer numbers out to do this calculation. So I went for 2 on the x-axis with 1.4, and I went for 4.2 on the x-axis with 2.6, and they seem to have worked out quite nicely. I can then do distance up divided by distance across, and I get about 0.55 for mine. Okay, so with your graph, I'll give you a couple of minutes. Hopefully you've finished your graph. Can you, from your graph, write down your intercept first of all on the y-axis, and then choose any 2 points on your graph that are reasonably far apart and have a go at finding the gradient. Okay, I'll give you a couple of minutes to do that now. Okay, hopefully you've got a gradient out now. It should be round about these, maybe not exact. You might get, for example, 0.34 or something like that, or 0.57 for your gradient. Those values should be okay. So, once we've got those, we need to think about what we can do with them. To do that, I just need to go back a couple of slides. We're going to have our equation here. Log y equals log k plus x log a. And what we're going to do, you're going to use your intercept and your gradient in order to find out the values of k and a. So for me, I've got the intercept of 0.35 and the gradient of 0.55. So if I say the intercept equals 0.35, then that means the intercept is this part here. That means I can say that therefore log k equals 0.35. So the intercept in this equation up here that we're plotting as a straight line is the log k part. And then to find k here, I can undo the log, write this as a power. Remember, this is log base 10 in here. Write it in if it helps. This is going to be 10 to the power 0.35. And I did that on my calculator earlier and I got 2.2. Okay, so we now know the value of k. We've got that. We can also find the value of a because we know the gradient of the line we calculated. For me it was 0.55, might be a slightly different calculation for you. That means that log a must equal 0.355. And then again we can undo the log by writing it as a power. We would get a equals 10 to the power 0.55, which on a calculator is approximately 3.5. And if we think back to what our original equation looked like, it was of the form k a to the x. And so now we can take our values of k and a and we can get an equation that should hopefully fit the data pretty well. It will be 2.2 times 3.5 to the power of x. So this is an exponential equation that we got from our straight line that should hopefully fit our data. Okay, I'll come back to this screen and leave this back up in a second. What I'd just like to do first though is show you how good a fit this line would be. So here are my original points and here is the line that I've just calculated from my data. Now it's not perfect, but it isn't bad in my opinion. We could maybe have got it more precise if we'd used more precise values here, but we have to take into account that the values in our table at the beginning were only two significant figures, so it might not actually get us any better by doing that. Another thing that's worth noting is there's something that's beyond the scope of our course, but you might meet it if you study maths further, and that's called linear regression. You can actually, at the stage where we had this graph here, you can actually calculate mathematically the equation of this line of best fit. And by doing that you can get more precise values for the gradient and the intercept from these points. Okay, but that's a bit beyond the scope of our course. Okay, so I'll just give you a couple of minutes to have a go at this for yourself. Use your gradient, your intercept, see if you can get an equation here. You might not get exactly 2.2 and 3.5, but you should get somewhere in that ballpark. Okay, just going to do a quick recap of the question now. Don't worry if you've not finished, but it means that other people can get on with the next question. So, a question like this is pretty long, and you may find in the exam it could be written like this, but it's more likely to be broken up into several parts, A, B and C, in which you would do these steps. There'd be like a step that said show that it can be written in this. Well, I'll just walk you through what the steps could be. This first part could just say show that it can be written in this form. So you take your exponential equation, write it in the straight line form where one axis is a log. Then it might say, from there, can you plot the graph of it? So then you would move on to this step here, and you'd do log of y, you'd get your values, you'd plot them on your graph. Okay, then you'd find your gradient and your intercept. That might be another part separately again. And then once you've got your gradient and your intercept, you'd use those to find your values of, in this case, k and a. Okay, so once you've finished that one, I would like you to have a go at question 1p on the PowerPoint. There's a full written solution on there for you to have a go at. If you haven't got graph paper, again, if you click the link where it says Desmos page, I'll show you what it looks like, the page you'll get up. Okay, you'll get a page that looks like something like this. I've put in all the y values here. What you will need to do, I've filled in one of the log y values. You need to plot your log y values in here. That will make them appear on this graph here. Once you've done that, click this button here and it will draw a line of best fit for your points. From that, you'll kind of have to do it a little bit more by eye. You'll have to try and figure out what 2 points are. It's a bit harder to do on the screen to get your gradient and your intercept, but I think it's still possible. Okay, let me know how you get on. Okay, so these questions are quite meaty, so I'm going to give people I want to say about 10 minutes, and then I'll check in with everybody in 10 minutes and we'll see how far people have got and whether it's time to move on. Okay, good luck with example 1p then. Okay, I've had about 10 minutes on that, but I'm really not sure how long it's going to take people to do, particularly as you're having to do it on your own without any help unless you email me. So, I'd be really grateful if anybody could email me and say I'm still plotting the graph, or I've finished, or I'm calculating the gradient, just some kind of thing to give me an idea of how far people are along. If I get enough responses through, that generally gives me a good spread of where people are at. Okay, thank you to the people that got back to me. Most people have said they're either getting towards the end of plotting the graph, or they're doing the gradient part. So I think maybe another 5 minutes or so would be sensible. I want to give people a chance to finish that. I realise it might mean some people are hanging around for a couple of minutes, but you're at home, so I'm sure you can find something interesting to do for the next 2 minutes while you're waiting. Okay, so I'll give people 5 more minutes to finish off this one then. Okay, I'm going to move on to the next question. I'll just show you what this graph looks like. It's not as good a fit this time on this one. Sometimes that happens. Sometimes it's the data doesn't work. Sometimes it's just you can't, from the data you've got, get a line that fits it really well. It's just how it is. But this is a reasonably good fit for this kind of data. It certainly works well at the lower end, maybe not so good at the higher end. Okay. In particular, when I created these questions, I didn't choose values that precisely fit onto an exponential curve. I modified the value slightly, which is representative of what happens when you collect data in the real world. It doesn't always fit nicely onto an exponential curve. Okay, so what we're going to look at next is we've seen x plotted against log y. Can we figure out any uses for a fully logarithmic scale where we plot log x against log y? And it turns out that actually we can, and we need to be able to do that as well. So in the next example, it's similar kind of thing. The procedure is pretty much the same, but we'll find that instead of plotting x against log y, it makes more sense to plot log x against log y in this case. Okay, so you don't need any graph paper for this one. This is one where you're given a straight line on a graph of log x to log y, and you're gonna work just with the graph that you can see. Okay, so we're told that the relationship between x and y is modelled by this equation up here. Oh, sorry, I've skipped ahead. It's modelled by y equals kx to the power of n. Now, this may at first glance look the same as what you did before. It's k times something to a power. But what you need to notice is this is not exponential growth in this one. When we did exponential growth, we had a to the power of x, and the x, the variable, was the power. This time, the variable is the base. Okay, so this is just called a power equation. These ones here, y equals, it's just x to the power of something. Okay, so it's going to be slightly different what happens when we take logs. So we have got y equals kx to the power of n. And like last time, I'd like you to have a go at this along with me. You should be kind of familiar with what we're going to do here. We're going to take, we'll take logs of both sides. I'll do that at the same time as you guys. Log y equals log of kx to the n. What I would like you to do, just the same as the last question, hopefully you won't make the moving the power down mistake this time. Use the addition rule and the power rule to split this apart and get rid of the power and see what you get. So I'll give you a minute or two to have a go at that, and then I'll write on what I've got and we'll talk about how it's different to the last example. Okay, hopefully you get something like what I've got on the screen at the moment. The key thing to notice here is how it's different to the last one. We've still got log y and we've still got log k. Those two bits are still the same as last time. But this bit here is not. Last time we didn't have log x, we had x. And we didn't have the other constant here. This was log for the other bit. So last time when we had y equals ka to the x, we had log y equals log k, those two bits were the same, plus x log a. So it's like these two bits have switched around. So how is that different in terms of what we would plot on a graph then? Well, in this one then, we would plot log y against log x, and this time when we do the gradient bit we won't have a log, we'll just have a number that equals the gradient, so that bit would be a little bit easier to do the calculations from. Okay, so we've done part A, we've written log y in terms of log x, that's all that part was asking us to do. Okay, in the next part then, we're going to try and write y in terms of x. So we're going to get an equation that's going to be, well, we're going to get this power equation of the form y equals k x to the n. That's what we're aiming to get at the end, something that looks like that with the values of k and n we will have found. Okay, so we've just done this down to this. That was our working out for the last bit. We need to now try and figure out the values of k and n. And we do that. We can't use the intercept as such in this. We use the gradient in the same way as before though. So the starting step here, I'm going to find the gradient. Okay, it's the distance up, so that will be 34 minus 2 divided by 9 minus 1, distance across. If I do that calculation, 32 divided by 8 gives me 4. I've chosen nice numbers for myself. Okay, now really we need to find out what this is. If we knew what this point was, we could just use it, but unfortunately because we don't know the intercept, we could figure it out, but we don't actually need to. What we can do is we can use our straight line equation, y minus y1 equals mx minus x1, although it won't be y and x, it'll be log y and log x here. Okay, so I'm going to use the equation of a straight line. Okay, here this first bit then, y minus y1. Remember, it's not y that's on the y-axis, it's log y. So we're going to have log y minus the y coordinate. I could use either, but I would rather use 1 than 9. Sorry, I would rather use 2 than 34. So I'm going to write log y minus 2. That's going to equal the gradient, 4, times x minus x1. But again, not x on the horizontal axis, it's log x. And that is minus the x coordinate, which is 1. Okay, let's expand out these brackets on the right hand side. We'll get log y minus 2 equals 4 log x minus 4. Then we'll add the 4 over to this side. That would give us positive 2 here. And I'm going to subtract the log to get it on the other side. So I'll have 4 log x minus log y. And then next up, I'm going to use the power law to tidy this up. So it becomes log x to the 4 minus log y. Then I'm going to combine these two logs together. If I've got a log, subtract a log, I can write it as a division. So log x to the 4 over y. Now I can write this as a power. Remember, this log here is log base 10. So I can write 10 squared equals x to the 4 over y. Then if I multiply up by y and divide through by the 10 squared, I get 1 over 10 squared, which is 100, x to the 4. Okay, so the equation of that original curve, if it's plotted on fully logarithmic scale, log x against log y, then we get a straight line. But if we wanted to plot this graph on xy axes, we would end up with a quartic, and it would be y equals 1/100 x to the power of 4. Okay, so we've written y in terms of x. Okay, there's a bit of a neater version here if you want something to write up. Okay, so make a note of that one, and then after that I'd like you to have a go at this one. It's a similar kind of idea, just with different letters, different numbers for yourself. Okay, once you've had a go at that, we've got 20 minutes, so that will probably only take you between 5 and 10. I've put in the PowerPoint the answers to the questions on the worksheet I mentioned earlier. So the worksheet, there's a link in the PowerPoint, a link on the course page, you can get to it wherever you want. Question 1 requires you to plot a graph. So if you're having a go at question 1 and you haven't got graph paper, there's a Desmos version of the graph that you can have a go at there. Questions 1 to 4, 2 to 4 are similar to the ones I've just done, so you don't need any graph paper for those. You could have a go at those without drawing a graph. Okay, so all of the answers are on the slides that follow. They're all mark schemes rather than written solutions for these ones. So once you've finished question 2p, have a bash at those questions. Okay, I'll be here probably for the next half hour or so, so if you do have any questions as you're going along, feel free to email me or send me some work, and I'll see what I can do. Okay, if I don't speak to you again on email, thanks for watching. Have a nice have a nice Easter holiday. This will be the last lecture for a couple of weeks. I'll send you an email before the next one. So thank you for watching. Have a good break. Okay, just a quick point. Somebody's pointed out the answer is wrong for question 2p. It's not the answer, it's just ended up being a different question. So I'm just in the process of fixing that now. So if you've got something different to what it says on the mark scheme, just hold fire for a couple of minutes and then I'll put the correct answer, well, what will hopefully be the correct answer up. Okay, here's a hopefully corrected version of question 2p part B. So check and see if this is what you've got. Be good if somebody can confirm this is what they did get, and then I can confirm with everybody that it seems to be right. If it seems to you to be wrong, please let me know. I've done it really quickly, so I might have missed something.